Naming complex substituents, that's going to be the topic for this lesson in my organic chemistry playlist. Now, we just went through an entire lesson on naming alkanes. We went through all the little rules and numbering the longest continuous chain and how to name the substituents and get the proper chain locators and which way to number it and all this stuff. But one thing we actually haven't covered, though, is what if you don't have simple substituents like simple methyl, ethyl, propyl, butyl, so type groups and stuff like that? What if we have what are called complex substituents? Well, it turns out there's going to be two ways to name them. So some of them have common names, and then there's always going to be a systematic name available, and that's what's going to be covered in this lesson. Now, if this is your first time joining me, welcome to Chad's Prep. My name is Chad, and my goal is simply to make science both understandable and even enjoyable. Now, this is my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new video. All right, so naming complex substituents here, and we'll start off with a simple substituent, and then we'll turn it into a complex one to make this harder. Now, if we look at our parent chain here, we can definitely identify the longest continuous chain pretty easily. That is our parent chain. And if we were going to number this thing to make sure that that substituent got the lowest possible number, it would be located 1, 2, 3, 4, 5, 6 from this direction, or 1, 2, 3, 4, 5, 6, 7. So we'd number it 1, 2, 3, 4, 5, 6. And I'll just number through the rest here. And this would be some form of dodecane here. So, and in this case, this would just be a simple substituent, just be an ethyl group, 2 carbons. No, not too bad, and it'd be 6-ethyl dodecane. Now, what if we make this 1 carbon longer? Well, now that's just going to be 6-propyl dodecane. It's still just a simple substituent. So, however, if all of a sudden I do that, we have a problem. So because it's not a butyl group would have added that carbon, just 1 carbon long, and it would have been a straight substituent, straight chain, we'll say. So, however, by making it branched, that's what actually makes it a complex substituent. And none of the names we've used up to this point would be appropriate for this. And so in this case, I'm going to stick one more off of here. And so the way this works, this is now no longer, again, a simple substituent. It's what we call a complex substituent. And we have a systematic way for naming these as well. And so up to this point, we've circled the parent chain in blue, and then we've got this lovely substituent here. Problem is we're also going to circle a longest chain for this guy as well. Now, when you've got one of these complex substituents, it's a substituent with its own branches, a branch coming off the main chain that itself has branches. What you want to do is identify the carbon that's attached to the main chain, and he's going to get the designation number 1. And starting with him, you want to start with him as number 1 and go through the substituent to get the longest continuous chain within the substituent. And so with him number 1, I can either go left and get to 2 here, or go over to the right and get 2 here, and I can get a longer chain going off to the right. And so I'll make him number 2. And then whether I go up or go to the right, either one of those is going to be number 3. And so I'm going to circle this guy as now the longest chain in the substituent. So a little tricky here. And that's 3 carbons long. And again, being a substituent, we'll name it with a YL suffix, a YL ending, and 3 carbons would be propyl. And then the way it works is then you name the substituents that are coming off the substituents, if you will. And in this case, they're both methyls. So we have 2 methyls coming off the propyl. And again, the key is don't call this propane because it itself is a substituent or part of the substituent. So we call it propyl. And so we've got some form of dimethyl propyl substituent. And so if we just want to name this substituent here, we see that we've got methyls at carbons 1 and 2. And so this would be called a 1, 2 dimethyl propyl group. Cool, and that's what the systematic way of naming a complex substituent here. Now, when you name a complex substituent, if you're going to put it into the actual name of the entire compound, then you always need to put it in parentheses. That's important. And the idea is that a lot of these complex substituents start with numbers. So, and then if you give the chain locator of where it's attached to the main chain, then you put another number at the beginning, and then you just get this garble of numbers. And it's like, well, which do you mean? Well, if you put the complex substituent in parentheses, then you know that the numbers inside the parentheses are part of the complex substituent, and the number outside would be the chain locator of the parent chain instead. And so if we name this entire compound here, this is going to be 6 hyphen, and then parentheses, and our substituent is going to be that 1,2-dimethylpropyl. So 1, 2 dash dimethylpropyl, and then the parent chain here again is dodecane, 12 carbons long. Cool. And that's how the systematic way, at least, of naming complex substituents. All right, so I know what you're thinking. You're like, Chad, you said we don't have to name anything longer than 12, and you're right. I just wanted to draw a really long parent chain so that everything coming off it's definitely going to be a substituent, but we're definitely not going to name this as a parent chain or anything. Our focus is going to be on the substituents I have coming off this parent chain. So first one I'm going to have coming off right here is this guy, and my question for you is, what would I name this as a substituent? Well, in this case, it's got 1, 2, 3 carbons, and so it would just be a plain old propyl group, and that is a simple substituent. Now, if you look at having 3 carbons here, and I'm going to kind of put them off here, just 3 carbons. So, and if I wanted to attach these 3 carbons to a longer parent chain, I've got 2 options. I can attach it through either of the end carbons, and that's what you get when you attach the propyl group here. So notice I'm just attaching that last bond. I'm just drawing it into one of the end carbons of propane. But I have another option. What if I attached it through that center carbon instead? And that's what you get here instead. And we couldn't call this a propyl group. And again, this is not a straight chain substituent. It's branched. And as a result, it's a complex substituent. Now, it turns out if for complex substituents, if they have just 3 or 4 carbons, you have an option. There is, turns out, a common names for these smaller ones. And you got to know those common names, or you could still use the systematic way we just talked about. So, but you got to know both. You're on the hook for both. Now, again, typically when you name it, if you're naming it and the question on the test that you're taking is you have to name it, usually either one is acceptable. But the problem is you might be given a name and then have to draw a structure. And so you got to be able to look at the name and then know how to translate that into a structure as well. So you do got to know both. You're on the hook here. So it turns out for 3 carbons, these are your only 2 options. It's just a regular plain old propyl group, or the only isomer of propyl that exists we call isopropyl. All right, so that's 3 carbons. Now, what if we add an additional carbon here? In fact, let's just start from scratch here and make it 4 carbons long. Now, let's start here. 1, 2, 3, 4. There. So now this is not a propyl group, it's a butyl group. But once again, we have a couple of options here. So there's 4 carbons. And if I attach this to the main chain from either end, that's how you'd get just a plain old butyl group. Okay. So, but my other options is I could attach it from the second one in from the left or the second one in from the right. And it doesn't matter which one I choose. It's the same thing either way. But that's going to lead me to another option. And so in this case, there's my 4 carbons. But instead of attaching it through one of the ends, I'm going to choose one of these 2 middle carbons instead. Now, if you look at these 2 middle carbons, these 2 carbons are each, and again, before it's attached to the main chain here, but they're attached to 2 carbons. And if you recall, we did a lesson classifying those, and those are called secondary carbons. So, and notice once you attach it to the parent chain, it actually turns into a tertiary carbon. It'll be directly bonded to 1, 2, 3 carbons, not just 2. But we're going to name this based on that root structure here before it's attached to the main chain. And so it turns out it's still got 4 carbons. We're still going to call it some form of butyl group, but we'll call it a sec-butyl group instead. And it's hyphenated, so sec-butyl in this case. So we have plain old butyl, and now we see that we've got a sec-butyl where it's attached through one of the secondary carbons. And again, it's named as a secondary carbon before it's actually attached. Once again, I attach it, it turns into a tertiary carbon, but the name comes from what it looks like before it's attached. So there's our sec-butyl. But with 4 carbons, it turns out we actually even have more options. Because with 4 carbons, not only do you have a straight chain possible, you also have a branched 4-carbon chain as possible as well. And so we have all 3 of these carbons on the ends, and they're all equivalent. And so if you attach it through one of these carbons on the ends, that's going to give you 1 structure. Let's see what that looks like down here as well. So in this case, there's that lovely structure. And whether I attach it to this guy, or this guy, it's all the same thing. And we'll go there. And so when you attach it to the 4-carbon branch structure through one of the outside carbons, that's what we call isobutyl. tert-butyl. And notice a difference here. Sec-butyl is hyphenated, whereas isopropyl and isobutyl are not hyphenated. That'll be important in a little bit. So, but that's isobutyl. And iso anything, it turns out, is going to be a straight chain that ends with what I like to say a fishtail. So it looks like drawing a fishtail to me, or some people just say ends with a Y. So you can have isopentyl, you can have isohexyl, and it's just a straight chain that at the very end forks into a Y shape, if you will. Cool, so that's our isobutyl group. But the other option would be attaching it to the middle carbon of that branched 4-carbon structure. And if you notice, we're going to do this similar to the way we did the secondary one. Well, this carbon right here is directly attached to 3 other carbons and is a tertiary carbon. And so we're going to call this tert-butyl, short for tertiary butyl. And so in this case, so that middle carbon there is like this one, and I've kind of changed the shape a little bit because that's how it would look when you actually drew it out and stuff. So, but that is your tert-butyl group. Cool. And so with 3 carbons, we just had propyl and isopropyl. But with 4 carbons, there's butyl, sec-butyl, isobutyl, and tert-butyl. And tert and sec-butyl are both hyphenated. Again, I'm pointing that out. It'll be important. So when you go up to 5 carbons, you actually have like 8 different versions, and we don't typically make students know those. Now again, these are all these common names, and they're totally acceptable. Now the reason I was pointing out the hyphenation here and stuff is how they're alphabetized. So it turns out these ones that are hyphenated, sec-butyl and tert-butyl, are actually alphabetized not by S or T, but by B for butyl. And the truth is, you're never going to have a sec-butyl and a tert-butyl in the same molecule. And if you did, I have no idea which one would actually win the tie from an alphabetical standpoint. I've never seen it happen in 20 years. So, but these others, there's no hyphens in them, and it's just the first letter. So for isobutyl or isopropyl, that they're actually alphabetized by instead. So definitely one thing to keep in mind there. You should also, again, realize that you could totally see the systematic names for these as well. So if we look at like the isopropyl, so there'd be carbon number 1, the one attached to the main chain. So again, keep in mind, there's our main chain. So I'll circle it just like we've done so it looks familiar. So there's our main chain, and then this would just be a 2-carbon branch that has another single carbon branch coming off the branch. And so once again, when you name it systematically, the carbon directly attached to the parent chain, that's carbon number 1. And then get the longest continuous chain in the substituent you can get from there. And so whether it went left or right, it was going to be 2 carbons. That's an ethyl group. And in this case, it has a methyl attached. And so if you look at your handout, right next to isopropyl, it's called a 1-methyl ethyl. So if we do the same thing for the sec-butyl group over here, again, this is going to be carbon number 1, and starting with him as number 1, I can number through 2, 3. My longest continuous chain from there is going to be 3 carbons long, and then I'll have a single branch coming off that branch, which again is a methyl, and so this would be a 1-methyl propyl group. Take a look at the isobutyl group, and again, carbon directly attached to the parent chain is number 1, and numbering from there, number 2, and then either one of these could be 3. And so it's a 3-carbon branch with another 1 carbon coming off it, another methyl. And this would, an isobutyl group could also be called a 2-methyl propyl group. And then finally for that tert-butyl group, again, the carbon directly attached to the parent chain is number 1, and then any one of these could be number 2. So I'll just choose him. And this one I'm going to write out real quick. So this is going to be called a 1,1-dimethyl ethyl group. Let's write that out. So you can see that on your study guide there as well. So 1,1-dimethyl ethyl. And again, if you were going to actually name it as part of a compound, complex substituents, when you name them systematically, always go in parentheses. If you use any of these common names, they don't go in parentheses. But when you name it systematically, that is when it goes in parentheses. And there's one other special case here you need to know, that when you're naming them systematically like this, because you get numbers in there and things get complicated, whatever the first letter in parentheses is, that's what it's going to be alphabetized by, even if it's part of a numerical prefix. So normally for regular simple substituents, we don't use the di, the tri, the tetra as part of the alphabetical at all. But for a complex substituent, whatever the first letter in the entire name that shows up in parentheses is, that's what it's going to be alphabetized by, even if it's part of a number prefix. So in this case, this will actually be alphabetized by the letter D in dimethyl ethyl. Cool. So now we've seen how to name our complex substituents, both in a simple way and a systematic way. And again, if you've got complex substituents that have more than 4 carbons in them, you're just going to only have the systematic way available to you at that point. So you definitely got to know both, like I said again. So now we've got a couple of complicated examples here that are both going to involve some complex substituents, and we're going to name them. So first thing you're going to do, same thing we've always done, is find the longest continuous carbon chain. So I can see here that from this branch point, whether I go off to the left or down below, it doesn't matter either way. So, and at this branch point, I can definitely see when I go left and when I go right, I can get 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, whereas here I'm only going to get 1, 2, 3. So the longest continuous chain does not include this guy. That's going to be part of a substituent, but it'll definitely include, and in this case, again, either down or across, it doesn't matter. And so then the rest are left to be substituents. So there we have an ethyl group. And there we have another ethyl group. But here we got a problem. And in this case, it's got 1, 2, 3, 4, 5 total carbons. You don't have any common names for something like this. So to name it then, you're going to have to number the longest chain starting with number 1 as the carbon directly attached to the parent chain. So there's 1, there's 2, and either one of these could be 3. And so this is going to be some form of propyl group with a couple of methyls attached. And so in this case, I can see that it's a 1,2-dimethyl propyl. And that'll go in parentheses. And so in this case, we're going to say diethyl is part of the name, but the di won't be part of the alphabet because these are just simple substituents. So it's going to be alphabetized under the letter E, but my complex substituent is going to be alphabetized whatever the first letter is, and D comes before E. So we're going to say the dimethyl propyl first. And in this case, if we number that longest continuous chain, I can go 1, 2, 3, or 1, 2, 3, and that's a tie. Okay. 1, 2, 3, 4, 5, 6 to the second substituent. 1, 2, 3, 4, 5, 6 to the second substituent, still a tie. So 1, 2, 3, 4, 5, 6, 7, 8, 9 for the third substituent. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 for the third substituent. And in this case, it's an absolute tie. So, and it turns out it's even more than that, it's just an absolute tie. This molecule is perfectly symmetrical. And so whether I have the ethyls at 3 and 9, well, the other way, they'd be at 3 and 9. And this complex is at 6. And no matter which way we number it, it's exactly the same thing. And so it doesn't matter. So I'm just going to go left to right because that's what I normally do. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, and in this example, you know, if you're from certain parts of the world, you're probably more likely to go right to left. And for a symmetrical molecule, it doesn't matter. All right, so we'll name the complex one first. Again, it comes first in the alphabet, and we see that its chain locator is 6. And so we're going to say 6 hyphen parentheses 1,2-dimethyl propyl. And the parentheses, and then 3,9 diethyl. And then our longest chain is 11 carbons, and recall that that is undecane. One big long word. All right, so one more example here, and yet again, our longest continuous carbon chain will definitely from this point 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. So it will definitely include these branches off here. And again, I could have circled this carbon instead of this one, and I could have circled this one instead of this one. It was arbitrary, they're totally equivalent. So, but I had to make sure that this is my longest continuous chain. It does not involve that. That's just going to be a substituent along with these methyl groups. So now this substituent right here is again a substituent that itself has branches coming off it. It's a complex one, but it only has 1, 2, 3, 4 carbons. Because it has 4 carbons, you could name it as a the common name for that complex substituent, or you could use the systematic way, and both are totally acceptable according to IUPAC rules. And so you really got a little bit of flexibility here. So we've got a couple of methyl groups here, but this guy could be an isobutyl. Notice it ends with the Y, so that's an isobutyl. Or that could be carbon number 1, and then 2, and then either one of these could be 3. And so your longest continuous chain is 3 carbons. That's a propyl group. And there is a methyl coming off that propyl. So that is a 2-methyl propyl. So let's write both of those out there. So this could be a 2-methyl propyl in parentheses, alphabetized under the letter M, or it could just be an isobutyl alphabetized by the letter I. All right, in this case, numbering this thing. So 1, 2 for substituents that 2 if we go left to right. 1, 2. So 1, 2, 3, 4, 5 for the second constituent. 1, 2, 3, 4, 5 for the second. 1, 2, 3, 4, 5, 6, 7, 8 for the third. 1, 2, 3, 4, 5, 6, 7, 8 for the third. Once again, I've given you a perfectly symmetrical molecule. It wouldn't make a difference which way you numbered it. So this time I'm going to go right to left just for the fun of it. Doesn't matter either way. It's going to get the exact same name regardless for this symmetrical molecule. Did I count that right? Did I miss one? 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. All right. So we can see that we've got methyls at 2 and 8. So, oh, this should be fun. So we've got methyls at 2 and 8. So we got something tricky here. So if you notice, methyl and methyl propyl, they both begin with methyl. Which one would come first in the dictionary? Well, methyl would come before methyl propyl because you'd keep adding more letters here. And so if you call this thing a 2-methyl propyl, you'll name the 2-methyl propyl second when you list the substituents. But if I call it an isobutyl group, I comes before M, and I'll name the isobutyl group first. So it actually matters which way you name this thing. So because the order in which you name the substituents is going to change. Now again, both names are acceptable. So, and you've got to be prepared for both. So let's take a look at this here real quick. So in this case, let's start with the systematic name. And in that case, again, methyl's going to come first. So we're going to say 2, 8 dimethyl. And then 5, 2-methyl propyl in parentheses. So, and I'm running out of room, so we'll just keep continuing this on. And 9 carbons would be nonane. One big word. One big word. Whereas had we named our complex substituent with a common name, isobutyl, then we would have named the methyls second and the isobutyl first. So this would have been 5 isobutyl and then 2,8 dimethyl. And once again, parent chain would be nonane. Cool. So just a lovely tricky example where, again, the order in which the substituents might change depending on if you use the common name or the systematic name for that complex substituent. Now, if you found this lesson helpful, please consider giving me a like and a share. Pretty much the best thing you can do to support the channel. And if you're looking for the study guides that go with these lessons, or if you're looking for practice problems on naming alkanes, so please check out my premium course on chadsprep.com.